Metalclad switchgear is one of the most popular types of air-insulated switchgear that we use on the distribution network. In this section, we will look at all the important aspects of this type of switchgear and how it is designed and operated safely under all conditions. By the end of this section, you will know all about vacuum circuit breakers and enclosures and components that interface with them. The aims of the course today are: introduce the ideas behind metal-clad switchgear, look in detail at circuit breaker vacuum contact bottles, introduce all of the features of metal-clad switchgear enclosures and the circuit breaker trucks that go into them. At the distribution voltage level, up to 36 kV, we tend to use three-phase vacuum circuit breakers that use vacuum bottles that contain the circuit breaker contact. Here we have a typical vacuum bottle. Let's look inside the bottle. It's got two terminals. One is connected to the fixed contact, and the other is connected to the moving contact. Here we can see how the two contacts come together. The circuit breaker spring-operated mechanism pulls the contacts apart quickly, usually in a time less than 20 milliseconds, and to a precise separation distance. The vacuum inside the contact chamber prevents the arc restriking after the contacts have been separated. Vacuum bottles were invented in the mid-1980s and have revolutionized the design of metal-clad switchgear, as they are smaller and less expensive than their predecessors. Before their introduction, oil tank circuit breakers were used and widely used for distribution switchgear, with the oil being used as an insulating medium and to quench the arc. The main disadvantage with this type of circuit breaker was that the oil that was used was broken down over time by the arc and became contaminated with PCBs, which are extremely toxic. One of the most common air-insulated distribution switchgear types that you will find is metal-clad switchgear. Here's some typical examples. These compact equipments are used indoors and house all of the required circuit breakers and bus bars inside a grounded metal enclosure. They come in many shapes and sizes. Let's look at the most common. Metal-clad switchgear is considered to be maintenance-free and very reliable. The instances of electrical breakdown are very low. The main cause of failure in my career is having rodents or insects getting inside the bus bar or circuit breaker chambers, shorting out the bus bars, and one instance of a bus bar support insulator failing due to a crack during manufacturing. Metal-clad switchgear normally use withdrawable circuit breakers, which can be removed from the metal enclosure to provide a point of isolation. Here's some typical examples of some withdrawable circuit breakers. Here's the normal symbol for a withdrawable circuit breaker. The withdrawable circuit breakers are normally referred to as trucks. Here's an example. Let's now look inside the truck to see what's going on. The first thing that we see is the vacuum bottle, which contains the contacts for the circuit breaker. This is connected through conductors onto contacts at the front of the circuit breaker. One of the contacts goes onto the main bus bars, and the other one connects to the individual circuit. On each of these main conductors, we have what's called a tulip contact, through which all of the current flows as it passes through the circuit breaker. These are spring-loaded and make sure that we make a good solid contact with a female connector on the main housing. To operate the vacuum bottle, we have a spring-loaded mechanism, which ensures that the circuit breaker contacts open quickly and to a defined distance. At the top of the truck, we have the secondary contacts. These carry all of the trip, close, and alarm contacts from the truck to the main enclosure. We have the manual open and close push buttons, which allow the operator to change the status of the circuit breaker whilst it's in the housing. And finally, we have the manual charging handle. This allows the operator to charge the mechanism's springs when the main power supply has failed. The truck goes into a main enclosure, which connects all of the main bus bars and other circuits together. This has numerous metal enclosed chambers, all electrically segregated from each other, so that if a fault occurs in one chamber, the damage does not extend to other parts of the housing. The first chamber is the secondary panel. This is normally on the front of the Metalclad enclosure and contains all of the protection relays, operational switches, and secondary circuits for tripping, closing, and monitoring the circuit breaker. Next, we have the busbar chamber. This contains all of the bus bars that connects all of the incomer and feeder circuits together. Here's a typical example. The bus bars are mounted on epoxy insulators to keep them away from the grounded enclosure. Next, we have the cable chamber. This is where we bring in the feeder and incomer cables and connect the switchgear to the outside world. Here's a typical example. Cable chambers can have one cable per phase or multiple cables per phase. The cables pass through the grounded gland plate at the bottom of the chamber. Inside the cable chamber, we also have current transformers, so that we can measure the currents on each individual circuit. If we need to measure the voltage, we provide VTs. These can be provided in the cable chamber to measure the voltage for each circuit, and above the busbar chamber to measure the busbar voltage. Finally, we have the circuit breaker chamber. You will see two shutters, a red one labelled busbar and a yellow one labelled circuit. These shutters are provided to stop anyone accessing the live busbar contacts and live circuit contacts behind them. Here's a typical example of the shutters. When the truck is inserted into the circuit breaker enclosure, these shutters open, allowing the circuit breaker contacts to interface with the busbar and circuit contacts. Let's now push the truck into the circuit breaker chamber. Normally, the truck can only be pushed into the enclosure so far by hand. From this point forward, the truck needs to be wound in using a winding handle. This ensures that when the circuit breaker contacts come into contact with the busbar and circuit terminals, it's done in a controlled way. As we can see, the shutters open, allowing access to the contacts behind. When the truck has been fully inserted into the circuit breaker chamber, the secondary terminals at the top of the truck make full contact with the secondary terminals for the panel enclosure. The panel now has full control of all the trip and close functions of the circuit breaker. Let's now add some cables onto the cable chamber and close the circuit breaker. As we can see, a circuit has now been formed, and current flows from the bus bars, through the circuit breaker, through the CTs, and onto the cables. Once the circuit breaker has been closed, mechanical interlocks ensure that it's impossible to withdraw the truck. Most Metalclad switchgear designs have different types of trucks. One option is a busbar grounding truck. When this is inserted into the housing, it grounds the bus bars. Obviously, before you can do this, all of the sources of supply to the busbar need to have been withdrawn. Another option we can provide whilst testing the circuit breaker is to provide what's called an umbilical cord. This connects the secondary terminals of the enclosure and the secondary terminals of the truck, and allows the truck to be opened and closed when it's outside the enclosure. The circuit and busbar shutters ensure that when the circuit breaker is withdrawn, the live busbars and cable connections behind them cannot be accessed. They are operated by mechanisms on the side of the circuit breaker enclosure. When the circuit breaker is pushed in by a fixed distance, the shutters open so the circuit breaker can engage with the live contacts. When the bus bars or cable connections are being maintained, the shutters can also be padlock closed to provide a point of isolation and prevent the circuit breaker being pushed into the enclosure. Let's now see how all these individual circuits fit together by looking at a plan view of the enclosure. Here's a typical signal line diagram for an 11 kV distribution circuit. At the top we have a 1250 amp incomer feeding a 1250 amp bus bar. We then have four 630 amp rated feeders coming off the bus bar. Let's see how these circuits are connected in practice. Firstly, we have the 630 amp feeder, with the circuit breaker chamber at the front and the bus bar chamber at the back. Let's now add the other circuits. As you would expect, the incomer is rated at 1250 amps, and therefore it's physically bigger than the 630 amp feeder circuits. To connect all the circuits together, we run a red, yellow and blue bus bar along the bus bar chambers. We've now implemented the circuit on the single line diagram. Let's now look at a more complicated circuit. On this arrangement we have two 1250 amp incomers, both feeding the lone 1250 amp bus bars. We also have a 1250 amp rated bus section circuit breaker, so that the bus bars can be connected together when one of the incomers has a fault or is out for maintenance. Let's see how we implement this circuit using our Metalclad switchgear. Firstly we have feeder 1, feeder 2 and incomer 1. We've now completed the first bus bar. For the bus section circuit breaker we need to do something slightly different. Because both bus bars 1 and 2 are at the same height, we need to bring the bus bars down through the circuit breaker and back up again. To achieve this, in addition to the bus section circuit breaker chamber, we need to provide another chamber called the bus section riser. Let's look at the bus section circuit in more detail. The first thing you notice is that both of the circuit breaker shutters are red. This is because we're connecting two bus bars together, and as you would expect, one is labelled bus bar 1 and the other one bus bar 2. In the bus bar chamber, we have the bus bars coming from bus bar 1 on the left, going down through the circuit breaker, and back up through the bus section riser chamber to bus bar 2. After the bus section riser panel, we now carry on with incomer 2, feeder 3, and feeder 4. We've now completed the second bus bar. We then run bus bar 1 all the way over from feeder 1 to the bus section chamber, and bus bar number 2 from the bus section riser chamber all the way over to feeder 4. We've now implemented the single line diagram. Metalclad switchgears are designed so that all of the live components are housed within grounded metal enclosures, but they do have serious issues with arc containment. When we have an insulation breakdown in an area such as the bus bar chamber, an arc will be generated between the live bus bar and the grounded enclosure. The huge amount of energy created by this event in a small volume will create a surge of high temperature air, which needs to be vented to prevent the enclosure exploding. We do this by providing arcing vents around the enclosure, which direct the arcing components and high temperature air away from any walkways to avoid danger to personnel. Let's summarise what we've learned today. Vacuum bottles are used widely on distribution circuit breaker contacts to contain the arc generated during both normal and fault conditions. Indoor Metalclad switchgears are used widely on the distribution network and allow for the connection of multiple incomers and feeders via common bus bars. Special precautions need to be taken with metal-clad switchgear to ensure that any arcs generated inside the housing are vented safely to avoid nearby personnel. Congratulations for completing this section. You should now understand all about metal-clad switchgear and appreciate all of the important aspects of this type of equipment. I've attached some questions on today's section to test your knowledge.